I just take the second half of the states that I've sampled so far, your bias is decreasing exponentially. Right? So I run my chain from time 1 up to t, and I just collect samples from t over 2 to t. And I aggregate with those. And then I have bias that's going down exponentially. This is sort of similar to what we'll do as test approximations sometimes. I think an interesting thing to do would be to see if there's a way of, because that's a single chain solution to bias reduction. Can you do a modification of that which gets you, for example, exact on biases? I mean, I think it's a lot more rigid because you just have the one chain and you need to do something different, maybe something like the real. That would be interesting. And to see if actually you can learn it once with that and get something meaningful would be kind of fascinating.
Yeah, for sure. Yeah, I can add too much to that, but yeah, it's an interesting question.
At some stage, you need to get a paper out,
right? Right. So big gains in variance if we increase the lag, like dramatically. So let's go back here. So around here, it's about up here. Right. Mean squared error about 1,000. Standard estimate, MCMC estimate of about 10, so 2 orders of magnitude. You increase the lag by factor of 3, you decrease the variance, the mean squared error taking n-1 by an order of magnitude, you're up to 100 here. Another factor of 3, another order of magnitude down to 10, and you keep on going like this. So here's the quadratic scaling I was talking about by looking at the y-axis. You can also see, so these are quantiles of the meeting times I'm plotting. Quite high ones, 90% to 99%, and they don't really change as you increase the lag, or not meaningfully so. They even stabilize at this point. So the point is that the meeting time distribution is quite stable, so you're not really paying much more of a price in excess of the linear cost from the lag. Yeah, as you increase the lag parameter. Right. Here's the TVD bound from lag 1, that's sort of off the top of the board, all the way to lag 300. You can see that it gets uniformly sharper as you increase the lag, which is, I suppose, unsurprising because the larger the lag, the fewer terms you you have in the triangle inequality, basically. You can also see that sort of by lag 10 already in the tails, where you should really care about this bound, it's already about as sharp as it can get, and it's sort of evolving to estimate into noise. At this point, if you pick your lag to be very big, then it is informative at every single iteration because the TVD is naturally upper-bounded by 1. But either way, you can get an informative diagnostic out of the bound at all lags, and they all say that basically converge by, say, about 150 to 170 iteration, which I should mention is in agreement with this. Yeah, here we are. Definitely.
Can I check with you with the earlier thing we had the estimating the transport distance? That's all agnostic to what the base metric is.
Yes, you just use triangle inequality, coupling inequality. That's it. And yeah, you can do P distances as well, but then you end up with like a sum of expectations, and you have to do each expectation separately, and then Jensen starts crying. But if you pick your lag to be big, then you're only estimating 1 term, so Jensen's no longer an issue.
I'm curious for a bit about whether you can use a mechanism to reverse engineer a metric which is contracting. So
you go back from the coupling construct, the bound construction here, and you try and get a coupling that's contracting.
Yeah, somehow. Because like with the TV, like something which is uniformly contracting, I should say. So with the TV, you see that it's not, and then eventually it is, right? And there's like, to go back to the stuff I was talking about, like, can you build a hybrid metric of the truth, which you show like, oh yeah, in the start, the spatial process is contracting. But it's going to be heresy at some stage.
Well, so okay, you're saying you pick your favorite sampler, you pick your favorite coupling, and then you do a bunch of these bounds with different metrics until you can see exponential decay, basically.
Something like that, yeah. Because if you wanted to estimate the spectral gap or something like this, in principle, it would be interesting. Like, you would have to restrict the space somehow. Like, say it's a linear combination of a few basic metrics or a function of a basic metric, etc. It could be kind of fun, but not necessarily easy.
I guess it's. I guess it's in the vein of sort of solving the Poisson equation with Markov chains, but it's sort of interesting for theoretical purposes. But you know,
yeah, potentially, yeah. So I think you could get maybe one or two useful things out of it, but not too much. There's got to be better ways of estimating this.
Word of caution. This is going back to what you said. You know, this isn't the panacea. Things can still go wrong. Just because this is an upper bound in expectation doesn't mean that for finite samples it'll be any good. So here's a bimodal target. I guess, there you go. That's one mode, and you can't really see this because the histogram's overlapping with it. But there's a second mode. The starting distribution starts way off over here. It's basically a spike. And you sort of, you do your lag, you start your second chain, and you run the couple of chains until meeting happens, and you calculate your bound. Job done? Well, not really, because if you pick your lag 1, that's this case here, then even with 1,000 chains, you see that all the meetings happen in the first mode, and that's because in this bimodal target with pretty small step sizes, the sampler really has problems moving from one mode to the other. So essentially, you have to increase your number of chains quite a bit until your second chain kind of somehow. So your X chain somehow miraculously, it's the second mode, and then before your Y chain has to then catch up with it to move to the other mode. So around sort of 5,000 and 10,000 replicates. These sort of finite sample bounds, you start seeing that indeed you get some chains reaching the second mode, and you get this second hump that indicates multimodality. But if you increase the lag, this is a ridiculously large lag of 18,000, I think, for this problem. Then bound at sample size 1,000, 5,000, and 10,000, they all look pretty similar. So in this case, we get an accurate picture of convergence. So you can still get very early meetings if the lag is low, and that is potentially a problem in multimodality. And indeed, if you have like a sampler started at a point mass with a high rejection rate, then you can just get stuck at that point. And the higher rejection rate is, then I guess the worse your life is. So I need to be careful. But the problem is fixed by increasing the lag, as this example shows, and indeed the theorem shows it as well. Because you reduce to the coupling inequality, basically, it's no longer an expectation, and an expectation sort of the tails can be arbitrarily bad, but the actual average can be reasonably small. In the probability, you no longer have this. Let me go back to it. You no longer have this, and essentially sort of meetings happen when they should. But it's a bit chicken and egg in terms of how you choose the lag, because you need to choose the lag to be big enough, and at that point you choose it big enough so that the exchange converges. So what are we really solving with the bias density? I don't know. But here we are. Right, so here's the guidelines for choosing the lag parameters K, M, and L. For convergence, really it just makes sense to pick L as big as possible. You get sharper bounds, and you also get some security in that in the coupling inequality limit, meeting times should happen where they should and not too early, so you don't tend to underestimate. For unbiased estimation, I think a good sort of guideline is to pick your lag as a large quantile of the meeting times, which is a bit chicken and egg, but you can do some preliminary runs and get a handle on this. Again, it's not perfect, because if you go back to this example, I mean, most of your meetings happen at, say, time 50. So if you pick that as a sort of high quantile of the meeting times, you'd probably pick it as 100, and again, you'd still be sort of stuck in the first mode. So again, careful. But if things go right and you can do this choice and it's fine, then it makes sense to pick sort of your burning parameter around same size as K. So your burning parameter K, same size as L. Because L kind of quantifies the bias in the X chain in this case, I guess. And you want to choose N as a fairly large multiple of L, if you can. That's so you have a bunch of terms, so you get a reduction in sort of length of chain, not just any chain in parallel. This is just a heuristic. It'd be nice if be some work that formalized this choice under realistic conditions. I'm looking at a sort of a semi-tractable example, just essentially coupled Ornstein-Uhlenbeck processes. We can get a handle on this, but nothing more than that. So that would be interesting to look at, I'd say. There's also the open question of, can the unbiased estimators achieve better mean squared error than standard MCMC for the same budget? Sort of, if you're somewhere in the elbow here, can you do better? I don't know. Maybe you can use some variance reduction techniques.
Can I ask you a question?
Yeah.
How does control bias work in this setting?
Oh, so I guess you could use it like for any sort of standard MCMC estimator. You just pick your favorite mean zero functional, you solve a linear regression, and you're done. But I mean, you could do it in practice like you have like 100 chains, 50 at the top, 50 at the bottom. You use you get some mean zero functionals from the 50 at the bottom, and you do linear regression versus the estimators in the first one, and vice versa. I mean, people propose this in the discussion paper, and it works, but it has nothing special compared to how you do it for standard MCMC estimators. So, it'd be nice if there was something specific for this construction that wouldn't come at much more cost.
Some people sort of interpreting the base estimator as kind of control variance in itself. Like if you shuffle around the telescoping zone,
yes,
it looks kind of like we're doing control variance.
Yeah.
Yes, and indeed you've got a free control variant, h of xt minus h of yt, guaranteed to have mean zero because the marginals are identical. But if you increase the lag, then the positions these guys are at is like one's here, one's over here. Say. So they're essentially independent. So they don't tell you much about what's happening in terms of variance.
And this is essentially but if the coupling is good, then you have sharper bounds.
Yeah. If the coupling is good, it's sharper bounds, the total variation, and better estimators, because you have fewer terms knocking around in the debiasing terms, smaller coefficients. So yeah, faster meeting equals better life, basically under this. Right. Cool. So. Plenty of time left. So far we've discussed, I guess, the basic idea of unbiased MCMC and estimating total variation bound with the same sort of coupling methodology. Ways of choosing parameters for the methodology that sort of give you good performance in terms of either variance or sharp bounds. I've discussed some basic couplings that kind of make things work under fairly mild conditions. The real question is how to design couplings that work in more complicated scenarios, say couplings that scale nicely with dimension, or I guess with samplers that sample on more challenging problems. So this is what I'm going to try and discuss now. The key idea is basically when you're in high dimension, you want to use a coupling that's contractive in the basically exact sense that Sam presented in the previous course. You also need to somehow combine it with a coupling that allows for exact meetings, because contraction isn't enough for this methodology. So you want to mix the two in a particular way. Right. So here's a sampler where the coupling is good in terms of it scales just as well as the underlying algorithm, the independent sampler. And Sam already presented this, but let's go over it again. Basic independence, metropolis kernel. You have a proposal density that doesn't depend on your current state. So that's just fixed. And for this, I'm going to introduce this weight function, which you can just think of as an importance weight. It's just the target density over the proposal density. And if you think of sort of the weight being big, that means the sample has a particularly high importance, or that the sort of, the target density at that point is much larger than the proposal density. And somehow these slow down the convergence and the mixing of the sample. Because if your proposal density was bang on, then the weights would be exactly one. Right, so standard Metropolis Hastings, you just propose a point, and then you accept and reject with the Metropolis Hastings test, which is, in this case, just reduces to the ratio of the weight of the proposal over the weight of the current state. And if you accept, then you update your state and off you go. There's connections between between independence, metropolis, importance sampling, and rejection sampling given by this weight here. In particular, this sampler is geometrically ergodic whenever these two kind of work well. So that's when the weight is uniformly bounded, and I think Sam made that assumption as well. So we're going to make this. In terms of achieving this, you want to use the heavy tailed rule. You choose the tail of Q to be heavier than the tail of pi. And sort of this is why sort of tempering ideas work in this particular case, because they ensure this. Right. The coupling that we'll use is kind of the obvious one. Because your proposal density doesn't depend on the current state, it just makes sense to propose the exact same point every single iteration. So we're going to propose the same point for the X chain and the Y chain. For the accept reject steps, we want to encourage them to be accepted at the same time because we want to meet right. So that we can just achieve by using the same uniform in the accept reject steps. And that's it basically. So this is your P tilde. One interesting thing about this is it's got a monotonicity property. So if say your weight at the state X is bigger than the weight, so weight at X is bigger than the weight at Y, then the chains coalesce as soon as the X chain accepts. And if you want to understand why that goes on, then you should just move, see, you move the weight from the bottom on the left-hand side, you've got the same W on the left-hand side, the same U, and then UWX is bigger than UWY, so if this is accepted, then for sure this is accepted. So that's where we are. And basically, if you use this coupling to sort of get direct sort of theoretical bounds on the TVD, then these are known to recover sharp rates. And this is just going back to what Sam was discussing before. Right. In terms of the L-lag coupling, we can do an extra refinement of setting the starting distribution to Q, which is kind of the natural one. I mean, you know, if you can come up with a better starting distribution than the proposal, then you should probably use it as a proposal. And we can also couple the starting conditions, so that will allow meetings at time zero as well. We can just use sort of the draw Y0 as the proposal that we use to draw XL. And this comes with the added benefit that if you exploit the monotonicity property, then these two chains coalesce immediately as the X chain accepts after sort of its first L-1 iterations. So for instance, if XL accepts, then bang, we're coupled at time zero. And the way this goes is, okay, well, if you believe me in saying this, then, you know, if you draw Y0 as the proposal used to draw XL, then you can pretend that you sampled Y-1 before Y0, and you just set the weights to be 0. So basically, sort of the Y0 proposal was immediately accepted. So basically, you end up with weight at XL always being bigger than weight at Y0. Right. And sort of, you know, you think of, okay, it's the independent sampler, why do you care about this in practice? Well, you can use any sort of SMC sampler as your proposal in the independent sampler. And instead of the weight, you'd have the normalizing constant, the unbiased normalizing constant estimate you get from the SMC algorithm. So this actually scales better with dimension than your bog standard independent sampler. It's also nice that, you know, the main computational cost here is, well, the weight evaluation and the proposal evaluation, but since you use the same evaluation, you use the same proposal in both chains, you only need to compute one weight. So basically, the computational cost running the coupling on this is exactly the same as running the coupling on just running one chain. So you're not paying much more of a price here. Here's a nice party trick that people seem not to have realized, but you can do, is basically, since you're only essentially sampling one chain and just keeping track of a bunch of weights, then you can sample meeting times at multiple lags by just sampling one long chain, keeping track of all of these proposal weights. And keeping track of the proposal weights. And basically, it's because you can do all of the acceptance decisions given this information. So yeah. So if you're sort of interested in using a particle filter, as a proposal in an independent sampler, then you can just use as big of a lag as you want, essentially, by just running long enough chains and then post-processing. Right. So that's the independent sampler. Let's move to more sort of vanilla, commonly used, I guess, metropolized samplers. The random walk metropolis, everyone's favorite. If you just use the vanilla independence, maximal coupling with independence proposals, sort of in all dimensions, and you increase the dimension, then this doesn't scale particularly well. People who have seen me talk about or random walk coupling will have seen this plot before. The y-axis for the meeting times, that is on a logarithmic scale. So basically, it scales exponentially with the dimension, which is not what you want, because you know that the mixing time of the random walk algorithm scales linearly. So clearly we need to do better. The intuition as to why this fails is basically, just do a little drawing. So this maximal coupling with independent residuals makes absolutely no effort to contract the chains whatsoever. And when the dimension is big, in sort of standard asymptotic land, then sort of your chains are sort of order d apart in squared distance, but they need to make smaller and smaller moves of size 1 over d in terms of proposal variance in each coordinate. So in practice, you know, your overlap between the two proposal densities is going to be absolutely tiny, and in fact, in this case, it's 0, or essentially 0. But you know, it goes down exponentially quickly as dimension goes up, and you can do simple calculations to show that. Yeah, that's why this happens. It's not great. We should do better. The lesson here is that couplings that only try to coalesce often don't scale well with the dimension. Instead, you need to consider contractive couplings like Sam did, and those do get much better vertical performance. And you know, once the chains are close together, you know, as you bring them by this contractive coupling, then you can make an attempt at okay, that shouldn't be contraction, that should be coalescence. Basically, you try and make them meet when they're close together. When they're not close together, just use something that brings them close together. Right. So let's go back to the random walk metropolis. You know, one way you could think of designing contractive coupling for any metropolis sampler is you want to bake in the contraction into the proposals, right? Well, if you measure contraction in, say, Euclidean distance, then you cannot do that for the random walk because you get no contraction. So really, what you need to rely on is the acceptance. I guess I should mention that the reason why you don't get contraction is because the random walk doesn't have a preference for direction. It doesn't sort of use the gradient to say that, you know, maybe you talk about sphere around the mode, and, you know, the gradient points inward, so you can somehow see that you get contraction if you move along the gradient direction by the same amount. Well, the random walk can't do that because it just picks the direction of random. So clearly we cannot rely on the proposals to get contraction for the random walk. We need to pay careful attention to the acceptance step. I won't go into detail about this, but in recent work, we've shown that you need to essentially bake in gradient information into the coupling of the proposals, and that's by paying careful attention to the acceptance steps, which is, I guess, a limitation for the coupling, but you know, as an upshoot, it works well in practice in all sorts of light-tailed, heavy-tailed scenarios. Right. For Mallet, so again, as the random walk, so Mallet makes smaller and smaller steps as you go up in dimension. So if you use something purely that attempts to coalesce and makes no effort at contracting, you won't do well. So again, you need to use a contractive coupling. You would like to, I guess, no, one thing you can think about is baking it into the proposals. The proposals are just OOLA steps, and Sam already showed you that these contract. You know, if your target is regular and your step size is small enough, the intuition is basically this. So, there you go. Your target lies outside. So your target is this thin spherical shell around the origin, say. And then what the Mahler proposal does is first it moves towards the gradient, I guess towards the mode, and then it does some kind of sparingly symmetric step. But since you use the same noise, then the extra z terms, I guess, point. This is a poor choice of direction. The extra z terms point in the same direction. So the contraction you get by this carries through. So you get almost sure contraction. Right, so you can guarantee that the proposals move closer together, but then you need to be careful because if you don't also accept both proposals or reject both proposals at the same time, then this contraction can break down because the x chain moved away, but the y chain stayed fixed. And on average, it will sort of move away when one chain accepts what the other rejects. So you need to be careful. This coupling does some effort into correlating these accept-reject decisions, but in practice, what you'll need to do is maintain an acceptance rate that's a bit higher than the mixing optimal one, not much higher. And this kind of strategy, say, keeping like 70% accept-reject, works well even in really high dimensions. So that's what I'd use in practice. All right, I should say, this doesn't allow for exact meetings. To get exact meetings, you can use the reflection maximal coupling because your proposals are Gaussian, so you can get some overlap there, make them meet exactly. So what you do is CRN when the chains are far apart, reflection maximal when they're close together, job done. This is the kind of scaling that you can expect. The different lines are different sort of constants in front of the step size, and then the step size is scaled sort of optimally with dimension. And you can see that meeting times go sublinearly with the dimension, which is about what you'd expect.
Can I ask you a question about the 57%? Is it heuristic or?
Oh no, that's Gareth Roberts' diffusion limit result.
Oh, okay.
But it's the more.
Yeah, but the higher acceptance rate. So you should have a higher acceptance rate than 57.
I think it's 57.4%.
No, I think he's saying
Not in for coupling.
the reason
Oh, yes.
we're working with the higher acceptance rate in practice is a heuristic.
Yes, that is absolutely a heuristic. Yes. Well, okay, right. So currently there is no work on this. I'm telling you that you can derive ODE limits under this coupling, assuming a Gaussian target, and sort of, okay, if you start out somehow in the tails and not near the mode, then you can scale your step size as sort of d to the minus a sixth, which is also optimal for like when you're exactly on the target. And in that case, you can show that for any sort of acceptance rate that doesn't go to 1 in the limit. Sorry, no, I should say no. In that case, yeah, you can show that the square distance between the chains is there in the asymptotes like this, basically, sort of away from 0, to an appropriate rescaling of the distance between chains and time. So the coupling does fail unless you pick an acceptance rate that is higher than that, i.e. you scale your step sizes smaller than what is optimal. So this is a heuristic, but you can push the dimension high enough where it becomes precise. But in terms of what I've seen in practice, at least for simple targets, you need to go up to like dimension 10,000 to see it, and then you can always get pick a higher acceptance rate to force the contraction to carry through, basically. Yeah.
What is a good acceptance rate that you find in practice?
Well, I don't think I've done enough experiments, but I think, I'd say like 75% is probably, gets the job done. But the lower the dimension, the closer you can get to this. But, this and HMC, which I'll touch upon in a bit, they just work. You just use CRN and they just contract and, but I'm sure like for challenging targets, here, the implicit regularity assumption is, I think, smooth and strongly convex potential. If that fails, then you might have issues. But I mean, I guess the theory says that you need to use some like reflection coupling, right? And then it's probably still okay. Common random numbers. So in this case, you just use the same Gaussian noise in the proposals. So I should clarify that.
How high is the dimension?
Okay, so for this, okay, right. So I mean, I've got like quick and dirty calculations for the ODE limits, and to verify them, I just looked at Gaussians, 10,000 is where this kind of breaks down. So, you know, I think that's, yeah, it's pretty high. Right, but, you know, up to dimension 100, definitely doing all right. Meeting times are around the order of the dimension. Right, HMC. So this, it's sort of well known by now, at least in more theoretical circles, that leapfrog discretized dynamics contract when they're sampled with the same momenta after assuming the step size and the leapfrog steps are small enough, the integration time is small enough, and the target is regular. The intuition I have for this is that sort of every leapfrog step is basically like a little OOLA step, and all of these kind of, so each and every one of these will push you towards the mode a bit, and the CRN bits make sure that sort of the contraction carries through. So if you chain a bunch of these, then you get contraction, even more contraction actually. So you can use the CRN coupling of the sort of the proposals for HMC, and that will contract. You know, you could also hope that they accept at the same time, and you know, if they're close together, they will. So that's okay. The problem with HMC is that you can't write down a transition density. So even though you can maybe contract by using this coupling, and you can do this pretty impressively in practice, then you cannot use HMC kernels to meet exactly. So one solution is you mix in something that you can meet with exactly. So you know, Pierre Jacob and Jeremy Hang have this paper in Biometrica where they just mix in an HMC that allows for exact meetings and, you know, job done. But what did I say? HMC? Oh, sorry. Yeah. Yes, random walk metropolis. The slide is correct. I was incorrect. I guess, you know, it's a bit unsatisfying, I would say. You know, you can do a bit better. You can mix in a mallet, but it would be nice if you could just use HMC to allow for exact meetings. So that's an open problem. I've spoken to Pierre about this, and he's got some ideas, but yeah, it's still a computation expensive solution. But technically, you can do this, at least theoretically. Right. So here's how the meeting times scale on average. You know, for mallet, they kind of go up slowly. For HMC, they're pretty flat, and that's dimension 10,000 there. I mean, admittedly, these are just standard Gaussians, but you know, with a variety of, with the same integration time and the variety of leapfrog step size scalings, yeah, it's pretty good, I'd say. So if you want to do something in practice, CRN couplings of HMC, the way to go. Right. So this was all from Metropolis samplers. Let's look at GIP samplers. Yeah, if you want to scale well for dimension for GIP samplers, I think we're nearing the end, so I won't take a break. You would want to use sort of a multi-scale coupling. So if you use a coupling that purely attempts to meet, then you have some issues because the obvious way to couple GIP samplers is you got two copies. There you go. There you go. These are the marginals. And the obvious way you'd copy it, you'd couple the GIP samplers is that you'd couple the first marginal, second marginal, and so on. So every coordinate separately. And if you use a coupling that purely attempts to make the change, sort of to get exact meetings but doesn't do any sort of contraction, then essentially you need to couple all of these consecutively. And if one of them fails, then the whole thing breaks down and you have to start again. So you can expect this to basically, eventually, the dimension gets big enough, sort of decay exponentially. And this is kind of what you see here. The one scale coupling for this GIP sampler here just attempts to make, I guess, get meetings in every coordinate. You can see meeting times go up exponentially as dimension increases. So instead, what you should do, same as for the random walk and HMC and mallet and HMC, is you want to use a contractive coupling. So typically, what works is a common random number strategy in every marginal. The intuition behind that is the sort of optimal coupling in one dimension, say under some kind of, I guess, let's say the Euclidean cost. That uses the inverse CDF function ran with the same common uniform. So that's roughly why CRN works for GIF samplers. And yeah, you'd use the sort of CRN coupling, type coupling when they're far apart to contract, and when they're close together, you use some kind of coupling that makes the chains meet exact. When I say close together, you should consider like the entirety, like all the marginals together to decide when you want to swap from something that contracts to something that allows for exact meanings. But if you do that, you can get pretty good performance.
Can you repeat the contractive coupling?
Sure, yes. So common random numbers, I guess, well, so it depends on what sort of structure you have in the marginals, but if you assume you just want to couple like, two univariate distributions, right? So I just want to, I guess let's call it mu and mu. Then, so the best thing you can do is this coupling. So yeah, yes, the same uniform, and you push it through the inverse CDF, and I think Matt mentioned this on Monday.
Is this a contractive?
Well, so it depends on your distributions, but it minimizes any sort of, I guess, transport distance, depending on sort of the structure.
I think as long as the cost is complex.
Yeah, that's the one, yes. But I mean, there's no... Yeah, I mean, I guess there's no guarantee it will contract, but hopefully it will. I mean, yeah,
it's like the best you can do in the transport.
well, I mean, yeah, because you can imagine, you know, like somewhere here and here, you know, maybe like your proposal density, something like this and this, or, you know, sorry, your marginal somehow, you know, maybe you're in the tails or something, I don't know, but you're not guaranteed to get contraction, but, you know, typically they'll be nice, and you'll be here and here, and, you know, you'd expect, you know, the mass on average to, if you couple properly, yeah, to moving closer, but yeah, there's no guarantee, but it often works. You can clearly see this for Gaussian GIP samplers, where CRN is kind of guaranteed to get you contract as long as, you know, the sampler is ergodic, and actually recovers like the optimal rate. Yeah, that's right. Right, so these are all for continuous cases that I've discussed so far, and maybe in these cases it's kind of, well, it's not obvious, but people kind of know how to track convergence, right? You've got all sorts of heuristics, you know, you can look at trace plots, you can look at statistics like R hat, which might give you some kind of inkling that things go wrong. But in the discrete world, it's less obvious what kind of summary statistics to track. So one appeal of these coupling methods is that you can get a handle on convergence even in more complicated state spaces. So for instance, for the icing model, you know, there's sort of the single site sampler just sort of flips states based on sort of what the state of the neighbors are, on like a 2D lattice, I guess. You know, the natural coupling of two single site samples for easing models just try and sort of moves sort of, I guess, the same state, I guess, state I in both chains, sorry, coordinate I, let's say, in both chains, either sort of to +1 at the same time or to -1 at the same time. It's pretty easy to do because they're just binomials. More complicated examples that have been considered in the literature is, so one of them is this Dirichlet process mixture model. Right, I've got quite a bit of time, so I can go into a bit of detail. Right, so the idea is that sort of in Dirichlet process mixture model, you're doing clustering. So you've got a few data points and you want to sort of group them together. The way the GIP sampler works is it picks up one data point and decides whether to keep it in the cluster that it was in before, move it to one of the other clusters, or create a new cluster separately for it. And this sort of sampler sort of implicitly works on the space of partitions because sort of there's no natural ordering, no ordering of the sort of labels that it cares about. So to get a coupling of samplers like this, you'd also want to work on the space of partitions. And there are metrics that are defined in the space of partitions that don't care about the ordering of the labels and sort of completely circumvent the label switching problem. And because it's discrete, you essentially, the marginals are just like sort of sums of weighted Dirac masses, and you can just calculate the optimal transport coupling between the marginals exactly by using linear programming. And if your number of data points isn't too big, then that is okay. And so the idea is it's very natural to construct a contractive coupling here, and it allows for exact meetings in very quick time. I won't show that, so how quickly that contracts or couples, but I'll look at the easy model. So this is, I think, a 32 by 32 grid at critical temperature. So basically, it has very high probability of either all, all points on the lattice. They are either all points up, or +1, or all point down, or -1. So high temperature, low temperature is what I meant to say. Yes. So you can see that you kind of see this bimodal structure from the coupling bound. You hit the first most of a duration 1,000, but then it takes another, 1,000 times as many iterations for you to transition to the second mode. This shows up in the coupling bound. But if you use parallel tempering for this example, then you can see that you do sample much more efficiently because your convergence is quicker. And this is revealed in the total variation distance bounds I showed you before. Right. So,
yes, just a last remark with parallel tempering. So you're coupling the chain on with parallel tempering.
yes.
When there are many states with temperature, and are you coupling all the states at once, or?
Yes. So you consider the whole ensemble as one chain. And your meeting is when the whole ensemble is coupled with the whole other ensemble, and then you subdivide that coupling into when you don't do swaps. So sorry, you want to do swaps at exactly the same time in sort of both ensembles, and you can enforce that pretty easily. When you don't do swaps, then you just look at every sort of level in the ladder separately.
Okay, and you try to.
Yes, you try to meet sort of all of them separately.
Oh, okay.
And then I guess if you get to that before the swaps, then you're good. In the swaps, you have to be careful because, say you've got a pair that's coupled, then you want to make sure that you try and swap that together, sort of move it down or up a level together. But you can work around that. In this case, it works because there are not many levels. If you have many levels, then it's hard to couple the swaps efficiently. So you're back into sort of this Gibbs sampler example that I showed you.
But in high temperature is easier to couple, right?
Oh, sorry, yeah. So this is low temperature. The single site sample that is low temperature. But yes, in high temperature, in the ladders that are at high temperature, yes, it's easier to. Yeah, good because the mixing is so quick. But definitely, like the more swaps you do, the harder over time you have. So I mean that's an open problem that we're discussing about like making the coupling work more easily without having to muck about with swaps. Right. So in terms of this, some ongoing research that is my own on the dimensional scaling theory for MALA and HMC, which looks like you need to include more information into the coupling than you do into the actual proposal. So for MALA, you need some Hessian information, so do you for HMC, at least in the Gaussian case. And you can show some ODE limits for this. But in practice, that's maybe not so bad because I show you that scales actually to high dimensions. So really, how high do you have to go to see things break down? But anyways, you can also think of, it's useful, this kind of method, especially the coupling bound for diagnosing convergence on state spaces that are kind of ugly, like manifolds. There's work on coupling MCMC methods on manifolds, specifically for manifold random walk. Which on a manifold is unintuitively not a local algorithm. And yeah. A few open problems that I think would be interesting is extending the methodology to adaptive samplers. Somehow this doesn't really lend itself to sampler that changes its step size as time goes on. I mean, even though if you could do the adaptation in some sort of more Markovian way, you'd want the step size to kind of converge to a fixed point, and it's it's possible, I guess, that the two chains end up at kind of different points. So I guess the idea is that it really doesn't lend itself to adaptive samplers, so it'd be interesting to see if you could extend it to be compatible with that. Obviously, more complicated algorithms, can you do unbiased MCMC with PDMPs? I don't know. I mean, coupling PDMPs seems pretty awkward, especially getting the exact meetings right, but here it is. And another one I've been wondering about is, can you do unbiased MCMC with an approximate sampler like ULA without introducing an additional truncation variable? So you can think of, you have one ULA chain, you sort of run for a long time with a smaller and smaller step size. So as the step size gets smaller, you get closer and closer to stationarity. So in the asymptotic limit, it's sort of targeting the right thing. And you have a second chain that kind of does the same thing and is sort of contracted with respect to the first one, but you can't really make them meet exactly because of sort of the differing step sizes introduced by the lag parameter. But you can get unbiased estimators still, and there's some work on this by introducing the truncation variable. So it'd be interesting to see if you can get rid of that and just do biased approximate samples. Right, so I think that's all I wanted to say. If anyone else has got some questions, I'd be happy to answer them. Otherwise, I think we're done.
Any questions?
If you have sort of your Markov chain as your position and the step size you're currently using, I guess you're imagining something where you deterministically decay the step size over time. I think if you have it as somehow I do a random number of steps at each step size, if you set that up the same way, you could probably couple the two chains to switch step sizes after quite a number of steps and sort of synchronize them. I thought about this in the context of adaptive samples, and it doesn't solve that problem, but it might solve this one.
Okay, that'll be good.
So are you facing similar problem with the HMC and PDMP since they don't have a density?
So I haven't tried PDMPs. I think at least one person working on it, on coupling PDMPs, but I mean, I imagine that under right sort of settings, you can get the PDMPs to contract, depending on the sampler you're using. So I guess that's not the challenge yet. It's making them meet, like you said. I suppose depending on the structure of your problem, you can maybe make them meet. Maybe you feel like PDMPs kind of get stuck in certain states, like you have a boundary or something. Maybe there you can make them meet exactly. But yeah, I guess that's the main issue, making them meet. But yeah, for HMC, you can do some kind of weird thing where you try and sort of invert the flow, the Hamiltonian flow, a discretized one, to sort of, like you feed in like two velocities, and you feed in two x's and one velocity, and you want to get the y velocity that recovered sort of the coupled trajectory in a way, and you can kind of solve that with Newton or something. That's what I discussed with Pierre. But it seems really inefficient. But that would let you get exact meetings if you account for the Jacobian.
Maybe one comment related to the PDMP study is like you were describing with the Gibbs sample example earlier.
Yeah.
That you have this difficulty of like you have to make many things agree at once. I think the PDMP is like an even more challenging version of that somehow.
Mm-hmm. Yeah, I mean, a way to get it. Could it be possible to look at coordinate-wise, so merge coordinates of the process and do it coordinate-wise until all the coordinates meet?
Yeah, I think you could try something like that, but it would somehow have a very different flavor. So, like with the Gibbs, it's like make them close, all of them close in space first, and then try and make them meet exactly.
Yeah.
Whereas because we're working continuous time with PDMPs, you don't even have the luxury of splitting it up like this.
Yeah.
But yeah, probably does something.
Has there been any work done on combining these unbiased techniques with something like yield important sampling?
So there's the independent, I guess, the PIMH paper, and I guess you could use an yield important sampling as a kind of SMC sampler, right? So in that context, yes. There's also follow-up where they try and do more complicated particle filters, and they just don't work because the coupling is complicated and it's hard to exploit any other structure that will let the filters contract, I think. So I guess the short answer is no, nothing past that.
I guess it depends what you have in mind, right? Is that in principle with AIS, it's already unbiased?
I mean, like the normalizing constant, things like that, sort of like your, I guess, the actual, like, because the way that you go from the reference to your target is that you're applying like a sequence of these like markup kernels, right? And these markup kernels are typically biased, or they're typically like not. Yeah, I guess they're not perfect, right? Like so.
Sure.
Yeah, like if you are composing like a sequence of these unbiased kernels, then you still get. Can you say anything meaningful there? Or is that?
It depends what you want to say. Because it's certainly true that normalizing constant estimate is unbiased. So it kind of depends on.
So I guess if the self-normalizing what's happening.
Yeah. So I think the sort of particle MCMC reference. There's also some stuff where they were sort of debiasing log normalizing constants. And I think that was more in the domain of stuff. Like there were special tricks needed somehow. It's just.
Like this was more like an informed question because it's. I feel like when it comes to these types of methods, you have like reweighting techniques, like metabolizing techniques. So obviously this has been with metabolism, but I want to know, I guess, when you're reweighting things, it's still valuable.
So those guys basically talking about sort of not doing exactly this, but sort of doing bias reduction for self-normalized important sampling by running an MCMC. So it's kind of doing the same thing as that thing.
Is that Jimmy Olsen?
Yeah.
Okay, yeah. I know you mentioned doing couplings for that, and I was thinking, no, probably not a good idea. I mean, you're already like you're doing the bias reduction, but if you do the coupling, you just introduce more variance.
So here's one more question, I guess. If you are if a practitioner comes and they have like their problems, like, when would you think that it's worth it for them to actually invest in these things?
Yeah, that's a good question. I guess it depends on the nature of the problem. I mean, if you're just going to throw HMC at it, then you can just do the coupling for free because, you know, there's so few steps. Okay, if the convergence is really quick, just generically, if the convergence is really quick and, you know, we know how to come up with a good coupling, then you might as well just do it because you get it for free. Yeah, if you have a really hard time getting a handle on convergence just because you sort of state space is very unintuitive, you have no summary statistics to track, then I would put some effort into coming up with a good coupling. But yeah, if you're just interested in, you know, I've got a standard sampler and I've got a GPU, so I want to run 2,000 chains in parallel and, you know, slash off some of the bias there, I wouldn't do this because I guess in part it's not amenable to that sort of vectorization. And because, you know, I guess the main insight I've seen from all the experiments I've done is that, you know, the gains you get are more in the sense of, you know, you can do this in a principled way rather than you get better efficiency, if that makes sense. So, I mean, for like, you know, for very practically focused couplings, there's like one where they couple like phylogenetic MCMC algorithms on phylogenetic trees, and they're like, there is no summary statistic you can look at. So, you know, for that sort of problem, for sure, like I put in time into this, but, you know, for more like, oh, this is going to revolutionize standard MCMC, you know, infinite gains with parallelism. Well, not really, but I mean, it's still a goal thing.
I also have just a curiosity. So, coupling two chains and not more than two chains. Is it like, is there a way to have maybe multiple chains and couple of all of them? Is there any advantage? Or coupling, I guess, the name coupling, just a couple. But can you do, I guess the telescopic sum that you showed at the beginning, you can express it as, you know, adding more terms and then having more than 2 chains and then trying to couple all of them.
Yeah.
Is there some work in this direction? Or?
So I haven't thought about that specifically too much, but I know there's some settings where they want to do something like this, but just getting a coupling of 2 chains isn't enough. So they do a coupling of 4 chains, plus a random truncation.
So what do you mean is enough that they don't mix?
Yeah, I don't know exactly. I think it has to do with sort of the estimator having finite variance. But I don't know the details because it really didn't look into it. But it's something like AJ Jasra has a bunch of work on sort of these unbiased estimates with random truncation, including that one where they do sort of ULA with smaller and smaller steps, and they introduce a random truncation, and it sort of somehow gets some biased estimates. So that's where I would look for that. But yeah, I mean, you know, for the kind of the vanilla construction, I don't see what sort of benefits you get for running multiple chains. I'll make a note that there's been work before where they couple sort of, you can think of like having one longish primary chain and you keep like trying to couple multiple chains to it. So, you know, you start off 2 chains from like an over dispersed distribution, and one of them is your primary one of them is your secondary one. Secondary one hits the first one at some point, and then you sort of regenerate the previous one, like you sample it again, you keep trying and hitting it, and then there's some sort of rejection sampler intuition that gives you sort of an upper bound on TVD. It's some work in the 90s, by I think Valen Johnson that looked into this, but as a bound, it requires you to essentially identify again what the sort of geometric rate of convergence is for the algorithm, so it's got some limitations. But potentially you can do something with like, you know, 3 chains instead of 2. That's much better than this, but I don't know.
All right. If there are no other questions, thanks again. And I guess we can meet for the people who want to